students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we'll be doing this chapter called as ray optics. Right? Let's try to see the refraction through a spherical surface. Let's try to see refraction at a single spherical surface. Let us try to see refraction at a single spherical surface. Now what we are going to do is we are going to take a section of a spherical surface. Let's consider a section of the spherical surface A, P, B. Okay. Now let us assume that let APB be a section of the spherical surface of radius of curvature R. APB be a section of spherical surface of radius R. Right? Now, if it's a spherical surface, let's assume that it is separating two mediums of absolute refractive index mu1 and mu2. Separating two media of refractive index mu1 and mu2, right? So let's assume that mu1 is the refractive index of one of the media and mu2 is the refractive index of other media such that mu2 is greater than mu1. Right, let's assume that refractive index of one of the media is greater than the other. Now, let us assume that C is the center of curvature. Right? Let's assume that let C be the center of curvature. If it's a curved surface, obviously it needs to have a center. So let C be the center of curvature. Right? Let us assume that C is the center of curvature of the curved surface. Let us assume that O is a point situated on principal axis. Let O be a point situated on principal axis. What is principal axis? It is a line that passes through the spherical surface without any deviation. Right? Okay, now let's consider this, let's show this point O here, right? Now let us assume that OP is the incident normal to the surface APB. Now if there's O, from point O, if I have to draw, there will be two rays that will be given out. One which will pass through the principal axis, one which will pass through the curved surface. So let us assume, let OP the incident normal is, let OP be incident normal let OP be incident normal to on the surface APB. So it is normal to the surface and therefore it is refracted to the other medium without any deviation. Obviously, since it is passing through the principal axis, it is going to pass through without any deviation, right? And therefore refracted into other medium, without deviation. It gets refracted into the other medium without deviation, right? Without any deviation. Let's assume that OQ is the other incident ray oblique to the surface. This is OQ, right? So let OQ be the other incident ray let OQ be the other incident ray oblique to the surface. Surface, right? In which case I can say that this ray bends towards the normal as it travels along. Now if it is going to move from one transparent medium to another transparent medium, it is going to bend because of refraction. Let us assume that it bends and reaches QI. Let's assume that this is the path that is traced by the light or point image, right? So the ray bends towards normal. The ray bends towards normal and travels along QI. Fine. Now the two reflected rays meet at point I and form a real image of object O. The two reflected rays meet at point I to form real image of object O. Right? Now, I can say therefore that, let us assume, let's get a couple of angles here. Let's draw normal to the surface. Right? This is my normal to the surface, in which case, guys, this angle will be angle of incidence. Right? Let's assume that this angle is alpha. This is going to be beta and gamma. Let's assume this is beta, this is gamma, and this is my angle of refraction. Fine. Now let's see that. Let I be the angle of incidence. Let I be the angle of incidence and R be the angle of refraction. The angle of refraction. Right? In which case I can say alpha, beta and gamma are the angles made by alpha, beta and gamma are angles made by QO, QI and QC with principal axis. I've shown you this in the figure. Right? In which case I can say that we've also said that mu1 and mu2 are the refractive index of the two media. Now I can say that the refractive index of the second media with respect to the first media, refractive index of second media with respect to first medium can be given by the formula mu is nothing but mu2 upon mu1. That is my refractive index of second media with respect to first media.
Which is
Right?
second media?
This is my, I'll show you which is the second media. This is mu1 and this is mu2. Refractive index of second media with respect to first
The
media.
ray which bends.
Where you have the reflected ray, refracted ray is the second media. Where you have the incident ray is the first medium. Okay? So refractive index of second media with respect to first media is mu2 upon mu1. I can also say by Snell's law, if I apply Snell's law says that refractive index is sin I upon sin R, right? That means I can therefore say that mu2 upon mu1 is sin I upon sin R. Mu was mu2 upon mu1, mu is sin I upon sin R. Therefore mu2 upon mu1 is sin I upon sin R. Therefore mu2 times Sin r is mu1 times sin I, right? Now, if point Q is very close to point P, if point Q is very close to point P, that means if I'm taking that angle alpha is very small, if point Q is very close to point P, in that case then I can say then the angle I will be very small, then all angles will be very small. All angles will be very small. That means in that case for very small angles we know that sine of the angle is equal to angle, sin I will be equal to I and sin R will be equal to R. If I substitute this in the above equation, I'll get mu2 into R is mu1 into I, right? Now, in triangle QCI by exterior angle if I apply exterior angle theorem, QCI by exterior angle theorem, or in triangle instead of QCI if I say QOC, let's consider triangle QOC. If I consider triangle QOC by exterior angle theorem, what is the exterior angle theorem? We've learned the exterior angle theorem in our previous class where we have the measure of the exterior angle is sum of the measures of the remote interior angle. That means the exterior angle I should be equal to alpha plus gamma, right? I can say also in triangle QIC or QCI, which I was taking before, by exterior angle theorem, exterior angle, measure of the exterior angle gamma is going to be R plus beta, right? That means I can therefore say that R is gamma minus beta. From this I can say R is equal to gamma minus beta. I know the value of I know the value of R. Substitute I and R in the equation which we have found, that is mu2R is equal to mu1I. So that will become mu2 instead of R. I'll get gamma minus beta is mu1I, alpha plus gamma, right? Open the brackets and simplify. So you will get mu2 gamma minus mu2 beta is mu1 alpha plus mu1 gamma. So in which case you can say that mu2 gamma minus mu1 gamma is nothing but mu1 alpha plus mu2 beta, right? So in which case you can therefore say that I could take gamma common here, mu2 minus mu1 is mu1 alpha plus mu2 beta, right? Once I have this, let's leave that equation there for the timing. Now, we have also learned something about how we can find out the length of the arc, right? Now guys, can we just see this? If this is the length of the arc S, this is theta and this is radius. We learned that S is equal to R theta if, right? So I can therefore say that length of the arc S is equal to R theta. Therefore I can say that theta will be nothing but S upon R. That means the measure of the angle is length of the arc divided by the radius, right? Now if we know that principle, I can say that assuming all the angles are very small, as all angles are very small, they can be expressed in radians. They can be expressed in radians. Why am I doing that, guys? Because I can use that formula S is equal to R theta only when the angle is in radians. Now, guys, let's consider this. What will be angle alpha? Length of the arc is arc QP upon radius. Radius there is going to be nothing but PO. Guys, length of the arc is equal to radius into the angle. Next, similarly, I can say beta is arc QP upon PI, and gamma is equal to arc QP upon PC. Right? Once I know the value of alpha, beta and gamma, I can substitute this in the previous equation. Substitute alpha, beta and gamma in previous equation. So in which case, instead of gamma, I am going to write arc QP upon PC, mu2 minus mu1 is equal to mu1 into alpha. Alpha is arc QP upon PO plus mu2. Beta can be written as arc QP upon PC. Arc QP is constant. And it can be cancelled. I can take arc QP as common. Once I take arc QP as common, I can cancel arc QP. Right? Do we get this in here? So in which case I can therefore say that mu2 minus mu1 upon PC is mu1 upon PO plus mu2 upon PC, or PC twice. Gamma is PC, alpha is PO, and beta is PI. Right? Okay. Now, once you have this, let's apply sign convention here. According to Cartesian sign convention, if I apply Cartesian sign convention, then what is PO? PO is nothing but the distance of the object from the lens. Distance of the object from the lens is written as U. Since it is to the left of the lens, that means it has to be negative, right? What is PI? PI is the distance of the image from the lens. So it is written as V. Since it is to the right of the lens, it is going to be positive. And what is PC? PC is nothing but the radius of curvature. Right in the beginning we have said, again it is to the right, so it is going to be positive. If I substitute these values, I will get the answer as mu2 minus mu1 upon PC. R is mu1 upon PO. PO is minus U plus mu2 upon PI, that is V. Right? So in that case you will have the answer as mu2 minus mu1 upon R. Here I could take minus sign common. If I take minus sign common, I will get minus of mu1 minus mu2. I am taking minus sign common in the numerator. It is nothing but minus mu1 upon U plus mu2 upon V. Right? Multiply throughout by minus. So I will get mu1 minus mu2 upon R is mu1 upon U minus mu2 upon V. And this is called as the spherical surface formula. Right? Do we understand the spherical surface formula? So, spherical surface formula is mu2 minus mu1 upon R is nothing but mu1 upon U minus mu2 upon V. Now using this, I can derive the Lensmaker's equation. Let us find out the Lensmaker's equation. Now, we have already found out, we've already defined a lens as a transparent medium bound by two sides of two surfaces. Right? I can say that lens is nothing but it is two sides of two surfaces. So when I talk about a lens, this is what I'm talking about. I have two spherical surfaces. When a ray of light passes through the lens, it suffers two refractions. And since it is made up of two surfaces, at each surface, the ray of light is going to suffer a refraction. Right? Now, in order to understand this, we need to make certain assumptions for deriving Lensmaker's equation. One, we are going to assume that the medium on both sides of the lens is air, whose refractive index is 1. So you have air here, medium, medium, air. So on both sides of the lens, we assume that the medium is going to be air, whose refractive index is 1. We also assume that the lens is very, very thin and the refractive index of the material of the lens is mu. Right? The third assumption that we make is, as the lens is very thin, all distances are going to be measured from the optical center P without any significant error. So what I'm going to do is, first I'm going to draw the principal axis. This is my optical center P. So all distances are going to be measured with respect to the optical center. So let's first write the assumptions down before I show you how the ray of light is going to move through this. Assumptions made in deriving equation, made to derive Lensmaker's equation. The assumptions that you have to make: A is that the medium on both sides of the lens, the medium on both sides of the lens is air. The medium on both sides of the lens is air, for which the refractive index is 1. For which the refractive index is 1. Okay. Second, we are going to assume that the lens is very thin. Lens is very thin, and the refractive index of the material, the refractive index of material is mu. The refractive index of the material of the lens is mu. And the third assumption that we are going to make is, as the lens is very thin, as the lens is very thin, I can say that all the distances are measured. All the distances are measured. All the distances are measured from optical center P. From optical center P. Okay. So these are the assumptions I'm going to make before I start with my derivation. Now let us assume that C1 and C2 are the center of curvatures and R1 and R2 are the radii of the curvature. Since there are two spherical surfaces, obviously there will be two center of curvatures and two radii of curvature. So you will say, let's start making the assumption. C1 and C2 are centers of curvature and R1 and R2 are radii of curvature. Fine, do we get this thing here? Now let's assume that O is a point which is situated on the axis of the lens. Guys, let's see this. O is the point which is situated on the axis of the lens, right? Now I'm going to start filling in the figure. As I fill in the figure, I'll go on writing what I'm filling in. right? So let's write this O is a point on the axis of the lens. O is a point on the axis of the lens, right? Now let's assume that OP is the incident ray on the lens along the axis. OP is the incident ray along the axis. We have to have two rays to get my image. One of the ray I'm going to assume which is going to be on the principal axis only. So let OP be an incident ray along the axis. Now since it is along the axis, it is going to pass without any deviation. OP is the incident ray along the axis and hence passes without deviation. It is going to pass without any deviation, right? Now let's consider another incident ray OA, guys. OA, right? So let's assume that another incident ray OA which is incident at point A. Another incident ray. Another incident ray is incident. Another incident ray OA is incident then at point A. Another incident ray is incident at point A and will be reflected along and will be refracted along AB. From A it is going to move to B, right, and refracted along AB. This particular ray is going to get refracted along AB. Now if the other surface was absent, this ray would have travelled further, cutting the principal axis. Now, right, we are assuming that only surface A is present. Now I am going to draw the diagram assuming that only surface A was present, right? I am going to redraw the figure assuming that only surface A was present, right? This is O, this is my P, this is point A. Now if surface B was absent, then this ray would have further travelled, cutting the principal axis at say I. It would have travelled and it would have cut principal axis at say I, right? Thus I would have been the point where the image is formed. So I can say that if surface B was absent, this ray would have travelled further, cutting principal axis at I. Thus I would have been the point where the image would have been formed. So I is the image formed due to the refraction of the first surface. I is the image formed due to the refraction of first surface, right? Now in that case I can therefore say that, let us assume that, now we said that on either side there is air. So in that case I can say for this surface I can say therefore mu1 is going to be 1 because light is, or the light is going to travel from air to the medium. Mu2 is going to be equal to mu, right? Distance of the object is going to be u. Let's assume that this distance, guys, is u, and where the first image is formed, let us assume that that distance is, say, v bar. Let's assume that u be equal to u, and let's assume that v equal to, say, let's assume that this distance here is, say, v, right? So in that case I could therefore say by spherical surface formula, let's assume this distance to be, say, v bar. Instead of v, I'm assuming that distance to be v bar. Now if I apply spherical surface formula says that mu1, which is 1, upon u minus mu2, which is mu, upon v, which I'm assuming as v bar, is mu1 minus mu2, 1 minus mu upon r. We'll assume this to be R1, first refractive index. So this is your first refraction that will occur. Okay. Now, let us now consider the second refraction. The second refraction is incident on the second refraction. First it is going to occur on surface A, and then it is going to occur on surface B. The second refraction of incident ray OA is at point B. Now I'm going to continue from where I've left. I'm already inside the lens. Inside the lens this has happened. Okay. Now I'm going to take the second surface only. Now I'll show you the refraction with the second surface only. Right? Now, the ray of light is already here, say I. Right? From here, it is going to hit the second surface and it is going to come back. Right? Let's assume that it comes back at this point, say I, where I have a I bar, where I have a real image. Now this distance we had already assumed as V bar. Let's assume that this distance is, say, V. Right? So here this is my second refraction on surface B. So when I join the two refractions, this is how it is going to appear. This is going to be I bar. This is I. This is going to be U. This is going to be V, and this is V bar. Right? So I've broken it up into the two surfaces. Right? Second refraction of the incident ray OA occurs at point B, not P. Occurs at point B, and therefore the ray gets refracted, and therefore ray gets refracted as Bi bar. That's my refracted ray. Now, right? Now, I can say therefore here mu1, the ray is already inside the lens. Since the ray is inside the lens, the refractive index of the first, now it is moving from lens to air. So my first medium will be lens. My second medium will be air. The distance of the image U is going to be V bar, and V is going to be equal to V. Now again apply spherical surface formula. If I apply spherical surface formula, spherical surface formula says that mu1 upon u v bar minus mu2, which is 1 upon v, is going to be equal to mu1 minus mu2. So mu minus 1 upon r2. Right? Now add these two equations. Adding the two spherical surface equations. Adding the two spherical surface equations. If I add the two spherical surface equations, I'll get 1 upon u minus mu upon v bar plus left hand side here is mu upon v bar minus 1 upon v is equal to 1 minus mu upon r1 plus mu minus 1 upon r2. Right? If I add the two equations, this is what I'm going to get. Now, this is going to be 1 upon u minus mu upon v bar plus mu upon v bar minus 1 upon v is here 1 minus mu upon r1. Take minus sign common, so this will become 1 minus mu upon r2. Right? Minus mu upon v bar and plus mu upon v bar gets cancelled. So I get 1 upon u minus 1 upon v, 1 minus mu common, 1 upon r1 minus 1 upon r2. Right? Do we get this thing here? Right? Now, let's leave that there. Now, if all the rays of light are initially parallel to the principal axis, after getting refracted from the lens, they would pass to a fixed point which is called as your focal principal focus, and the distance would be called as focal length. I can say that. Let's leave this equation here for the timing. Rays parallel to principal axis after refraction meet at a point called principal focus. Right? Do we get this thing here? Now, in such a case, the distance of the image, therefore, v would be equal to the focal length. The distance of the image would be equal to focal length. Thus, for all the rays parallel to principal axis, all rays parallel to principal axis, u will be infinity because they are parallel to principal axis, and v will be equal to focal length. After passing through the lens, they will come and meet at a point, principal focus, and that distance is called as focal length. Substitute these values. So instead of 1 upon u, I'll get 1 upon infinity minus 1 upon f is 1 minus mu 1 upon r1 minus 1 upon r2. 1 upon infinity is nothing but 0. Therefore, I can say that 1 minus 1 upon f is 1 minus mu 1 upon r1 minus 1 upon r2. Take minus sign on the other side, in which case I'll get 1 upon f is 1 minus mu can be written as, if I multiply by minus mu minus 1, 1 upon r1 minus 1 upon r2. Right? That means mu, I have my answer in terms of, okay. So you will get this as, since I want this, 1 minus mu 1 upon r1 minus 1 upon r2, substitute this in the above equation. So I can say therefore substitute in above equation. So I'll get 1 upon u minus 1 upon v is minus 1 upon f. 1 upon u minus 1 upon v, all this can be written as minus 1 upon f. Take minus sign on the other side, so I'll get 1 upon v minus 1 upon u is 1 upon f, and that is called as my Lenzmaker's formula. Right? Do you understand Lenzmaker's equation? So Lenzmaker's equation says that 1 upon f is equal to 1 upon v minus 1 upon u. Right? Now, do we understand this? Okay. We'll stop this here for the day. Thank you very much.